Today we will start with coordination compounds. Normal compounds, you know, NaCl, FeSO4, or COCl3, like this. Here Na balancing 1, chlorine balancing 1, Fe 2 plus, SO4 2 minus, CO 3 plus, so Cl minus, Cl minus, Cl minus. So here minus 1. So this is called the primary balancing. Primary balancing is, till this time we were talking only valency, valency, valency. Now I am specifying that primary balancing. That means one more is coming, secondary balancing. You see this primary balancing of cobalt is plus 3. Primary balancing of cobalt is plus 3. That can be satisfied by chlorine. How many chlorine? 3 chlorines. Now I am going to write a compound. You will see in square bracket C2, which is connected to 6 ammonia. 6 ammonia, and ammonia is neutral. Ammonia is neutral. We learned ammonia is a Lewis base, Lewis acids we know. There in acid base, in that case neutral, that is not the way here. This is negative, positive or neutral. There it was acid base neutral. Here it is negative, positive, neutral. For example, Cl minus is a negative species. And K plus is a positive species. In that way, ammonia is a neutral species. Neutral species. So acid-base salt, in that case, in that we learn ammonia is a base, weak base, Lewis base. Now I am talking here in this chapter, negative, positive or neutral. So we say ammonia. Ammonia, we know it is a nucleophile because it can donate a pair of electrons. A species which can donate a pair of electrons, we know it is a nucleophile. Here we use the term ligand. Ligand. Ligand means the one which donates. Ligate. Ligand, the one which can ligate, means donate a pair of electrons. So you can call this ammonia as ligands also. Ligands can give a pair of electrons. 6 ammonia will be giving one pair of electron, one ammonia, one pair of electron, next ammonia, one pair of electron. The 6 ammonia can give 6 pairs of electron and make bonds. Means this is a transition element, you know, it has got vacant d orbitals. So that d orbitals, to the vacant d orbitals, this ammonia can donate one pair of electron. That d orbital is after hybridization only. After hybridization only, this ammonia can give pair of electron. That we will learn when we learn the hybridization. We'll be learning such things. Now, this is neutral, so this total will be having plus 3. That can be neutralized by Cl minus, Cl minus, Cl minus. So what do you see here? This is a coordination complex. A coordination complex. This is a coordination compound. Coordination compound. When you put this in water, you will get from here Cl minus, Cl minus, Cl minus. But this will not be separated in water. This will be remaining intact like this only. Like this only. Means we say primary valencies are ionizable. Means by putting in water, these primary valencies are are detached, ionizable, dissociated. But secondary valencies are non-ionizable, means by putting in water, this ammonia will not get detached from this cobalt. Like this, you see, this is a big thing I have written here. Like this, you must have seen the double salt. Double salt, that is, for example, you know, more salt with which you did a titration. Titration came on for you took in burette and the conical flask you put more salt, that is FeSO4 dot NH4 twice SO4 NH4 twice SO4 dot 6H2. This is a double salt. This is a double salt. This, by putting in water, this also looks very big while writing. When this is put in water, you will get all the signs: Fe2 plus, SO4 minus, NH4 plus, NH4 twice, SO4 minus 2, then 6H2. This is more salt. FeSO4 dot NH4 twice SO4 dot 6H2. So double salt when put in water, all ions get dissociated. But when coordination complex is put in water, only primary valencies are ionizable. This box format will remain like this on the box. So that means you know that around the cobalt there are six ammonia, six ammonia molecules. Six ammonia molecules means it will be like this. The structure will be like this. That is cobalt at the center. Here one ammonia, one ammonia up, and one ammonia down. This is ammonia. This is the actual structure. Ammonia. Ammonia. Means each ammonia will be making a bond. Actually, we call it as a coordinate bond. Nowadays, covalent bond and coordinate bonds are considered same. So, these are directional. Covalent bonds are directional. So, this is not directional. This is ionizable bonds are not directional. Ionic bonds are not directional. But here it is directional. So, which shape? Which shape? The shape is these are not bonds. Shape is what? Octahedral shape. So coordination complexes, the octahedral shape. And this CO star is plus 3, that plus 3 is neutralized by Cl minus Cl minus Cl minus. So coordination complexes have got this, see what is written inside this square bracket. We call it as coordination endarity. Coordination endarity. That has got a shape. The structure what I have shown here, that is octahedral. It may be tetrahedral if the hybridization is sp3, you know, tetrahedral. Then sp3d, then trigonal bipyramidal. sp3d, that is 1 plus 3, 4 plus 1, that is 5. So trigonal bipyramidal. D2sp3 octahedral or sp3d2 octahedral. So according to the hybridization of the central metal atom, this is called a central metal atom. Central metal atom or central metal ion, because this is CO3 plus central metal atom, or you can call it a central metal ion inside this coordination entity. According to its hybridization, the shape will be changed. So sp3, if it is sp3, tetrahedral, sp3d, that is trigonal bipyramidal. sp3d2 or d2sp3, that is octahedral. So this is a coordination compound. Coordination compound. In coordination compounds, there is a central metal atom which is connected by coordinate bonds, or you can say covalent bonds. Coordinate bonds means ammonia. This bond is made by two electrons donated by, ligated by this donor atom, ammonia, donor, ligand. There are 6 ligands around this cobalt 3 plus. What you see inside this is the coordination entity. This is called the central metal atom. These are the ligands, central metal atom charge. That is the oxidation state of the central metal atom. That is plus 3. This is not a coordination complex. That is a double salt. That is more salt. What are the differences between double salt and coordination compound? Coordination compound, when put in water, you will be getting, you will be getting only primary valences. For example, the CONS in the same example I think. If you put in water, only the primary valences are ionized. If I write like this is non-ionizable. But in the case of more salt or double salt, all the constituent ions are ionizable. So in coordination complexes, there are two valencies. One is primary valency and the other is a secondary valency. Primary valencies are ionizable, means by putting in water, these ions will be separated. But secondary valencies are non-ionizable. This is given by Werner, and so we call it as Werner's theory. According to Werner's theory, in coordination compound, the metal atom, central metal atom, shows two valencies, primary valency and secondary valency. What is primary valency? What is secondary valency? And the secondary valency is fixed for an atom. In the case, the secondary valency is 6. Secondary valency is 6. In the case of nickel, secondary valency fixed. Fixed means 4 and 6. 4 fixed, 6 fixed. Platinum, 4 fixed, 6 fixed. Then FCO, that is 6. So these secondary valencies are fixed. Then let's see what is written in the square bracket. That is called the square bracket. That is called the coordination entity. Coordination entity is having a shape. I told you central metal atom. What is the central metal atom here? That is CO. Now ligands. What are ligands? Ions or molecules bound to central metal atom. I showed the structure. Ions or molecules, here it is molecule, NS3. NS3 is a molecule which is bound to the central metal atom. It can be ions. It can be ions. How can it be ions? You see, this is, if I remove this 3 plus and write Cl. See, ions, here ions are outside. If I write another coordination compounds, that is NS3 5 times Cl. Secondary valency 5 plus 1 6. But here this is minus 1. So total this is plus 3. Cobalt is always plus 3. So plus 3 minus 1 means here plus 2. So that plus 2 can be neutralized by Cl. I am again reducing one more ammonia. MS3 4 times. Secondary valency is fixed, no change. So I put chlorine here inside the box. So there it will be, see, plus 3. This is plus 3 minus 1 minus 1. So here it will be plus 1. That is neutralized by only 1 Cl. Now look at these things. Secondary valency is fixed. Now if I put this in water, I'll get Cl minus Cl minus Cl minus. If I put this in water, I get Cl minus Cl minus, because this will not be ionized. If I put this in water, I get only 1 Cl minus. Suppose if I treat this with AgNO3, silver nitrate solution. Silver nitrate, suppose 1 mole of this thing I have taken. 1 mole of this thing I will be taking. I'll get 3 moles of AgCl, excess amount of AgNO3, enough amount of AgNO3. But I'll be getting only 3 volts of AgCl. What I get here, 3 volts of AgCl. But here, see, only this thing is ionized, so this only this can react with this excess Ag, so 2 volts of AgCl. Here I'll be getting 1 mole of AgCl. So what does this show? Outside only 3, outside here outside 3 Cl minus, here outside 2 Cl minus, here outside 1 Cl minus. See, secondary balance is 6, 4 plus 2 6, 5 plus 1 6, this is 6. Inside the coordination entirety, what is present, that will not be ionizable. Here you see negative ligands also. This is only neutral ligand, neutral and negative. There can be negative ligands also. Yes, ligands. What are ligands? The ions or molecules bound to the central metal atom, the central metal ion in the coordination entity are called ligands. It may be simple molecules like NS3, or simple ions like Cl minus, Br minus, I minus, or larger molecules like this. We call it as ethane 1,2 diamine. Ethane 1,2 diamine. If same functional group is present, then complete hydrocarbon name is required, ethane. 2 carbon atoms, ethane. Ethane 1,2 diamine. It is abbreviated as En. So it's not electron, En. Electron is represented by this. En means ethane 1,2 diamine. Suppose this is the ligand. It can make a bond using this pair of electrons. At the same time, it can make a bond with this pair of electrons. So, one ligand can make 2 bonds. Let's see, in the case of cobalt. This bond is made by this NH2, where a gola gives CH2, NH2. So using this pair of electrons, it has made this bond. Using this pair of electrons, it has made this bond in this way. So it makes a ring. We call it as chelation. Now you see. From down to this end, this is NH2, CH2, NH2. So using this pair of electrons, it has made this bond. Using this pair of electrons, it has made this. Similarly here, NH2, CH2, NH2. Chelation. This is means ring structure. The chelation gives stability to the molecule. This is what En, ethylene diamine. So ligands may be smaller ions like Cl minus, Br minus, or neutral molecule. Ligands may be negative ions like Cl minus, Br minus, I minus. It may be neutral molecules like NH3, H2O. H2O is a ligand. Or bigger molecules like this ethane 1,2 diamine or ethylene diamine. Or, so you know this is NH3. NH3, suppose I replace these three hydrogens by CH2, CH2, NH2, CH2, CH2, NH2, CH2, CH2, NH2. Now each nitrogen is carrying a pair of electrons. Here, this bigger species, two pairs of electrons. In the case of ammonia, one pair of electron, or Cl minus one pair of electron, Br minus one pair of electron. This is called monodendate ligand. Monodendate ligand. We call its density is one pair of electron. Density. Its density. This is didendate ligand. Didendate or bidendate. Bidendate ligand. Bidendate ligand. Density is 2. Its density 1, 2, 3, 4. Tetradendate ligand. Tetradendate ligand. This is monodendate, didendate. Now, how can we make it tridendate again? Here, it is CH2, CH2, NH2. This is tridendate 1, 2, 3. This is tridendate ligand. Tridendate ligand. Now, what is meant by a ligand? Ions or molecules? See, ions or molecules bound to central atom in the coordination entity are called ligands. Unidendate ligands, or monodendate ligands, didendate ligand or bidendate ligand. Then we can say polydendate ligand, tri, tetra, etc. Polydendate ligands. A ligand which is bound to central metal atom through several donor atoms. I'm going to write the most important, that is hexadendate ligand. Hexadendate ligand. That is EDTA. Ethylene diamine tetraacetate. Ethylene diamine tetraacetate. What does ethylene diamine mean? That is NH2, NH2, CH2, CH2, NH. I'm replacing this hydrogen by two bonds. It is acetic acid. I'm going to connect acetate, COO minus. CH2, COO minus. Here again I am replacing these two by CH2, COO minus, CH2, COO minus. Now you see one pair of 1, 2, 3, 4, 5, 6. This is a hexadendate ligand. Just like octopus has got 8 portions to get attached. It has got 6 portions to make bones to get locked with the central metal atom. This will give you, like this curving, this will again give you a lot of chelation. Chelation gives stability. EDTA is very important compound. Hexadendate ligand. So question used to come like this. Write the structure of a ligand whose density is 6. Write the structure of a ligand whose density is 6. That is EDTA. Now this is a chelate ligand. What is meant by a chelate ligand? When a di or polydendate ligand uses 2 or more donor atoms to bind a single metal atom or metal ion. That is called a chelate ligand. Chelation means ring structure, just like octopus locking the central metal atom from 8 sides. When a di or polydendate ligand uses 2 or more donor atoms to bind a single central metal atom, that is called a chelate ligand. The number of chelating groups in a polydendate ligand, that bind to a single metal ion is called dendricity. So dendricity means monodentate, didentate, tridentate, like that. Now let's move to ambidentate ligand. Ambidentate means same ligand, but it is ligating or donating or making the bond using two different atoms, same ligand. That we are calling it as ambidentate. Just like our ambident nucleophile, we learned ambident nucleophile similarly, that is NO2. N O O. This nitrogen can do the donation. Donation we show by this arrow. It's only nitrogen is used center metal. This is N. So this NO2 can donate from nitrogen side. Then we call it as nitrito N. Nitrito N means N is the donor site or donating site. Or if to the center metal atom, if oxygen is donating, that is O N O. This oxygen stone pair is donating, is getting donated. Then we call it as nitrito O. Nitrito O. If the ligands are negatively charged, then we will be adding O in the end. Chloride, not chloride, chlorido, bromido, iodido, nitrito, cyanido, cyanido, like that. Ice, thiocyanato means this thing will be ending with O. If the ligand is a negatively charged ligand, if the ligand is negative, then we say the name is to be ending with O. Chlorido, fluorido, like that. Okay, here we are saying ambidentate ligand. Ligands which can donate to different atoms. Same ligand, NO2, here NO2, here NO2. Same ligand which can donate through different donor atoms. Such ligand is called an ambidentate ligand. Now, secondary valency is also called coordination number. Next term, coordination number. The number of unidentate ligands attached to the central metal atom. The number of unidentate ligands connected to or attached to the central metal atom is called coordination number. In the case of the cobalt, that coordination number is 6. Next, we are going to coordination polyhedron. Coordination polyhedron means that shape: octahedral, tetrahedral, square, planar, etc. Now, oxidation number in central metal atom. Oxidation number of central metal atom in the coordination entity or coordination sphere. That square bracket is called coordination entity or coordination sphere. Now, I'm stopping.